Hello everyone and welcome to a new discussion which we are going to have on groundwater flow and flow nets we will be also discussing under this groundwater engineering course. So, we are now going towards that 3-dimensional flow to better understand the entire gamut of groundwater flow in 3-dimensional conditions. So, for 3D flow or 3-dimensional flow, the specific discharge, that is small q, may be considered as a vector quantity, and in that sense we are going to have a equation which is q equal to q upon a, that is capital Q upon a equal to I q x j q by and k q z. So, here you can see that q x is here, q y is here and q z is also here, and these are the 3 dimensions, and these A is the area, cross sectional area which we are seeing here. So, where I j k in this above equation represents the standard unit of vectors of Cartesian systems. Cartesian system means the north, south, east, west, north, east, south, west, that kind of thing. So, here the q equal to, again the same equation is written here, to that we individually we can write that the q x equal to capital Q x upon a. Similarly, small q by can be written as capital Q by upon a, and small q z can be written as capital Q z upon a. So, we can write separately also. So, in case of 3-dimensional flow which we are discussing, if the formation is homogeneous and isotropic, and though we have also discussed that this is a very rare condition that we get the flow, a homogeneous formation is homogeneous and isotropic, but anyway we start with the simple conditions and then we develop further on this, and so that if the formation is fulfilling these two conditions, that is homogeneous and isotropic, and groundwater is a uniform density and viscosity. So, it is a steady uniform flow, all kinds of things are there. The components of the specific discharge vector, are each given by a form of Darcy's law. So, now we are bringing here Darcy law which says q x equal to minus k capital X and dH upon dx. So, in case of simple 2-dimensional anisotropy as given above, that is in that case k x can be k y also. So, all these 3 equations for x, y and z can be written like this to fit into Darcy law. So, this form of Darcy law can however be applied only in cases where all 3 principal axes used in the analysis. If we are having that kind of information, and then only we can apply these 3 equations. So, these 3 principal axes is shown in the previous cube figure x, y and z. Further, it is important that generally rocks are neither homogeneous and nor isotropic. This I have already told you that this is an ideal situation in theoretical situations. Yes, you can assume all the time, but in real situation it is never encountered that rocks are or formations are homogeneous and isotropic. So, they are means heterogeneous and isotropic, and therefore, the q x, q by and q z will vary. That means the discharge from different directions, if I consider, then it is going to vary, because in all 3 directions the rocks are not going to be homogeneous and neither isotropic. So, how to manage this thing? So, the groundwater, as we know, that moves in accordance with the hydraulic gradient, and that is the point from high head to the point of low heads. So, these are the right side figure is called flow nets, in which we try to understand not only the cone of depression, but what are the other locations, like like here the first one is pumping well, another one is the recharge well, and third one is the discharge. that is discharged towards the into the river. So these nets would have a complete different shapes and sizes. So the groundwater moves in accordance with the hydraulic gradient, that is from high point to low point. So in case of recharge, that means the you see these arrows are going away, whereas in case of discharge the arrows are coming towards the river. And similarly, in case of pumping, the nearby arrows are going towards the well, but otherwise they are going away from there because the drawdown has not reached to that level. So the contour lines on the water table and piezometric surface maps, which is on this right side figure, connect points of equal heads. So all the the isohydrals are the contours basically. So wherever the head is equal, like in if I take in the center point where recharge, then it is marked, a contour value is also marked. So the movement of groundwater is perpendicular to these lines. As you can see, the dashed lines are showing in this contour map or flow net map. Dashed lines are showing as direction of flow of water, which are roughly perpendicular to the contour lines. So this one will remember for future uses of flow nets. So in many areas, many times it is not possible to obtain sufficient data to construct water table or piezometric surface maps, as you have seen in the earlier. So what we try to do it, that we use the water table altitude at 3 wells to determine direction of groundwater movement. So it's basically a 3-point problem by which we can identify the direction of groundwater flow or the groundwater movement. So here, as you can see that after having the values of from 3 wells, these lines have been drawn, which are indicating of different depth in the water. So here this, say for example, this is 27.6 if I take unit as feet, then it is 27.5 and this is 20. That means water will flow from higher grounds to lower ground. So by which you can know what is the direction of movement of groundwater. So however, the general direction of groundwater movement in such areas can be determined with the measurement can be made in 3 wells, and they say, as I have just mentioned, solving 3 points problem. This 3 points problem is useful in many cases where we do not have continuous observations and we do not have in the central area any observation whatsoever. So how to get the vector, that is the flow direction. So here it is, as it is already shown, that the direction of groundwater movement is, if I say this is north, then from north to south. So likewise we can, without much data also, just 3 wells data would be sufficient to know locally that what is the direction of the movement of groundwater. Further, the direction of movement of groundwater is only one of several hydrologic facts, and that can be determined from water table or piezometric surface maps. So what are other facts which we can do it? Like for example, movement of groundwater radially away from an area in all directions. As you can also see that in this case because this is recharge well, so water is recharging the surrounding areas and therefore these arrows are going outward, radially away from an area in all directions which I have just shown. These are all in outward directions, indicating that recharge occurs. So that means if these perpendicular lines, perpendicular to the contours are representing the equal water levels. So if these perpendicular lines are going away from the well, then that well is nothing but a recharge, or that area is showing a recharge. And reverse to this, if these lines which are perpendicular to the contours or piezometric lines or surface towards a well, like in this case it is towards a well locally, then it is the pumping well, it is taking out water from the aquifer. And similarly, in case of a discharge is happening in the river, then these will not be coming to one point, but rather than they will have a spread all along the river, but will join perpendicular to the direction of flow of the river. So this one has to remember that these arrows will indicate whether the well is the area is a recharging area or discharging area. So these flow lines tend to radiate from the center of a recharge area, as we have discussed in this case, and however not possible to determine the limits of the area from water level contours. So because every time whatever the survey is being done or whatever the data is available, it is for a limited area, and therefore it is not possible to go beyond that area for which the data is there. But however, some guesswork can always be done. If I am having sufficient details about an area, then some information about adjacent area can be said, but it won't be very highly reliable. Anyway, so it is better to before we do go or further in such unknown areas, the better is to understand the geological and topographic maps or geologic conditions of the area, whether they are similar or different in two adjacent areas. If they are different similar, then probably we can extend these contour lines like here. We can extend them like this, keeping the same trend, may allow delineation of areas in the adjacent areas. So the convergence of flow lines, as we have seen in this in discharge area case, the convergence of flow lines from different direction indicates the location of discharge area. But in case of a discharge happening to the river, then it is not the convergence. These will be coming perpendicular to the direction of flow of river. So such convergence generally occurs toward the stream or lakes into which groundwater is discharging and around a spring and pumping wells also. So the convergence of these flow lines in areas remote from natural discharge points indicates the position of pumping well or a change in geologic condition. For example, beginning of a limestone cave. So all the time it is not necessary that these convergences are because of pumping well. There might be some special geological circumstances or setup, like limestone cave can also have a similar kind of contours. And so that is in the karst topography, estimating groundwater occurrence and how much water is available, what would be the yield, well yield and other things for a karst area or a limestone terrain is always challenging and difficult. Anyway, we will be discussing further on that aspect. So now these flow nets that we know through flow nets the groundwater moves along flow lines and that cross equipotential lines, that is contours at right angles. So each flow line may be viewed as an impermeable boundary because adjoining flow lines are either side parallel to it or therefore no flow across it. So what it is that flow is not across these flow lines. Flow is not across these flow lines, it is only along the flow lines. And further, if selected flow lines are drawn on a water table or a piezometric surface map at approximately the same distance apart as the equipotential line, the spaces between them will be square. So that means that this space will be, if it is perfect, then it would be going to be square, but in natural conditions it does not happen. Anyway, so it means if no water is being added or withdrawn from the aquifer of the area, the amount of water moving through different squares is equal throughout the area. So that means that neither withdrawal nor discharge is happening. But this is truly an ideal condition. In natural conditions, as just mentioned, does not happen like this. So there actually this square shape box between these flow lines and contour lines will not be there. So in actual practice, these equipotential lines or contour lines are seldom parallel. They are not parallel and equally spaced throughout an area. Why they are not parallel? Because we know that this aquifer or these are neither homogeneous nor isotropic. So, they are heterogeneous and isotropic vertically and horizontally both directions. Therefore, it is not possible to have contour lines parallel to each other except in purely theoretical assumptions. So, differences in spacing are caused by differences in the permeability or thickness of an aquifer. So, basically the shapes of contour lines and shapes of flow lines basically they are directly indicating about the permeability or thickness of an aquifer, and therefore, these spaces bounded by equipotential lines or contour lines and slow line and flow lines, instead of slow it should have been flow lines, are also seldom perfect squares. So, rarely you would find, if they are square, that means just after having this plot of flow nets, one can immediately conclude that there is neither any discharge or nor recharge. But as we have discussed, it is not like that in natural conditions. So, flow net, as we have just seen, that is a graphical representation of two-dimensional steady state groundwater flow. So, steady state flow conditions are there through the aquifer. So, these will work only in such situations, but if we go in some other situations, then may not work like that. So, construction of a flow net is often used for solving groundwater flow problems where the geometry makes analytical solutions impractical. So, otherwise if it is not possible, then flow nets can provide insight about this. Now, here this is a aquifer and a flow net is shown here on the right figure, and these flow lines are shown in the blue color, and these green lines are the equipotential lines or contour lines which you are seeing, and in this as you can see that these flow lines are moving towards the well. So, if this is the situation, then the well is nothing but a discharging well. Immediately looking the flow lines, one can understand, but the shape is not circular, neither these flow lines are parallel. So, you can see here that there is a impermeable barrier is there. Here is a perennial stream is there. So, as we have also seen that this stream is recharging the groundwater regime. Therefore, these flow lines are going away from. In our earlier example of flow net, it was just a reverse case. So, the flow net approach is generally used in civil engineering, groundwater hydrology, soil mechanics, etc., as a first check for problems of water flow or flow under hydraulic structures like dams or sheet pile walls. So, flow net is applicable in many areas which you are seeing here also. So, a grid obtained by drawing a series of equipotential lines or contour lines is called flow net. So, this method of flow nets consists of filling the flow area and stream and equipotential lines. That means these barriers, this is another important thing which I want to emphasize here. This is the barrier in sense that it is, though sometimes it is getting water influent, sometimes it is effluent. So, this in this case this is influent, this is providing water to the aquifer. In case of effluent, this will be coming towards the river. So, these serves as barriers, and therefore, indirectly or directly I would say they are controlling the shape of your flow nets. So, that these barriers are important. If we do not consider these barriers, then our estimations about the groundwater conditions will be not very accurate. So, the method consists of filling the flow net area with stream and equipotential line which are everywhere perpendicular to each other, making a curvilinear grid which you are seeing on right figure. So, typically there are two surfaces or boundaries which are at constant value of potential or hydraulic head, that is the upstream and downstream ends. So, often these surfaces are no flow boundaries, that is impermeable, which we have discussed with the previous figure. Here also impermeable part is shown here. For the example of bottom of a dam, if it is like that, and top of an impermeable bedrock layer which define the sides of the outermost stream tubes. So, here also you can see that outermost stream tubes can be there. So, this is we are basically seeing in section form. So, mathematically the process of constructing a flow net consists of contouring the two harmonic or analytic functions of potential and stream functions, and these two functions satisfy the Laplace equation, and the contour lines represent lines of constant head, equipotential lines, and these lines tangent to the flow paths, that is streamlines or flow lines. So, together the potential function and the stream function form the complex potential, where the potential is the real part and the stream function is the imaginary part. So, there we consider like this in a when discussing through the mathematical part. So, with this I end this discussion about flow nets and flow lines or groundwater flow, where we can identify using flow nets where are the recharge areas, where are the discharge areas, whether river is effluent, influent and so on. So, with this I end this discussion. Thank you very much.